Welcome to Module 4 of Political Statistics. In the last module, we discussed levels of measurement and measures of central tendency. We spent time talking about the decision-making process and when each level of measurement and measure of central tendency might be useful and when it might not be. In this module, we'll talk about discrete and continuous distributions, common ways distributions misbehave, and how to tame them when they do. We'll also discuss how to interpret variables that have been tamed and what you should look out for when doing so. Let's get started. Political scientists tend to really like using statistics. Of course, good political scientists also use a rich qualitative toolkit as well, but overall, statistical methods dominate the field. Why is this the case? Well, for one thing, many phenomena political scientists are interested in occur often or at a scale that produces numerous observations. For example, some political scientists study the outbreak of war between countries. One way to measure that concept is by taking all pairs of countries that existed in a given year and seeing if they were engaged in large-scale armed conflict. Turns out that dataset is pretty gigantic. For the sake of demonstration, assume that each year, for the last 50 years, we've had 190 countries. So, one row per country pair per year. That's 190 countries, choose 2, combination, not permutation, the order of the countries doesn't matter, times 50, which equals 897,750 observations. And since we might be interested in the causes of war, we might observe the total amount of trade flow between our pairs of countries, for example. Now, unless one of your parents is an actual silicon wafer, it's unlikely you'll be able to make heads or tails of all that information by simply mulling it over in your head. As noted in the last module, we use statistics to summarize because it's not possible to process that much information by ourselves. One of the first ways we might try to summarize is to visualize our data. We've already talked about doing so for nominal and ordinal variables. We simply counted up the observations in each category and plotted them. In doing so, we were visualizing the distribution of responses across our categories. And since we're working with nominal variables, where there's no rank or order information encoded in the values, ggplot just put the variables right next to each other for easy comparison. Of course, we need to make sure we don't interpret that chart in a way that infers rank. We're not looking at trends here as we move from right to left, just the relative proportion of each value observed for our variable. But say we want to visualize a continuous variable in the same manner. How would we go about doing so? Take GDP, for instance. We wouldn't want to count values like we did with a nominal variable because no two countries have the exact same GDP. So we'd just end up with a totally uninformative chart that tells us next to nothing. Instead, we might move down the ladder of measurement and categorize our GDP variable into discrete ordinal categories. To do so, we'd need to set some thresholds and define buckets. Well, our minimum and maximum values are $55 million and about $21 trillion for Tuvalu and the United States, respectively. So why don't we start off by setting our bucket size to $100 million? That way, all countries between $0 and $100 million will be grouped together, all of those between $100 million and $200 million together, and so forth. Let's go ahead and plot that. Well, that's not very helpful. Why are most of my values bunched up way the hell over near 0? And why does my chart extend so far out when there's essentially no information out there sans 1 or 2 observations? We know from looking through our GDP values that there's a lot of variation, but looking at this chart, you wouldn't think so. GDP is the classic case of a misbehaving variable. It deals in large numbers, and it's fairly skewed. And you can see both dynamics at play in this chart. For one thing, interpreting the scientific notation on the x-axis requires a lot of mental energy. It takes me a minute to figure out that 1E13 is 10 trillion. For another, the two values for the United States and China are way bigger than any other observation in the dataset, even if we exclude those, and why would we anyway? The top 5 to 10 values are orders of magnitude bigger than the rest. So how do we tame this variable? Well, one way might be to descend further down the ladder of measurement and group by percentile. We might group all countries with values in the lowest third of observed values as low GDP, those in the middle third as middle GDP, and those in the highest third as high GDP. Or we might go a bit more fine-grained and do it by deciles. Countries between 0 and 10% of the observed values go in Group 1, 10 and 20, Group 2, etc. But in doing so, we've lost a lot of information about the spread of those values, and we've grouped together countries that conceptually don't belong together. South Korea, with a GDP of $1.6 trillion, is in the same group as the United States, which has a GDP of about $21 trillion. The latter is over 10 times more than the former. No, we need something a little bit more robust. So let's try to tackle our problems one at a time. First off, let's try to reduce the scale of our problem. Our numbers are just too big. All those extraneous zeros are impeding our ability to analyze this data meaningfully. So let's start simple. Let's divide by some big constant so that our big numbers get shrunk a bit. In fact, instead of just picking some random big number, why don't we pick a meaningful big number? Let's pick the smallest value in our dataset. Tuvalu's $55 million is still a big number. Well, that's a little bit better, though it didn't quite do the job as well as we'd hoped. But there are some benefits of dividing by the minimum value like we did. Most importantly, it's that we can interpret this variable in a relative sort of way. Since we've changed it, the unit of this variable isn't in dollars anymore. Instead, it's in multiples of Tuvalu's GDP. So a country with a value of 2 has twice the GDP of Tuvalu, for instance. Then again, the United States has a GDP 400,000 times that of Tuvalu. Our scale problem remains. What we need is some function that will squish big values more than it squishes small values. If you recall our last module, we needed something to do the opposite of that when we were calculating the variance, and we ended up squaring our values to accomplish that. So let's try the opposite. Let's take the square root of our GDP values and see what we get. All right, now we're cooking. More of the variation among the values in the bottom 80% of our data is showing up as that cluster starts to spread out, and our extreme values are getting more and more squished. It seems like we're on the right track, and maybe we just need to squish a little harder. So let's take the fifth root. And okay, we're really starting to get there. But let's take a step back for a minute and try to interpret this chart again. Some things are better. The x-axis is in numbers I can understand, 0 to about 500, but the unit isn't easy to wrap my head around. I don't often think about the fifth root of a country's GDP. Maybe I've been watching the wrong news channels, but I've never heard a newscaster refer to the fifth root of GDP, or The Economist write about it. I don't really have the mental scaffolding necessary to contextualize the scale. Moreover, those pesky huge values are still stubbornly outside of where I'd want a well-behaved distribution to be. So, better. Not great, but on the right track. So, we need a function whose output is easy to interpret, and it's likely that function will be similar to a root function. So, let's think about those two things in turn. First, what is it that's actually interesting about the variation in GDP? Well, the fact that it varies across so many orders of magnitude. Countries with GDPs in the single-digit billions are probably really similar, and countries with GDPs in the double-digit billions are probably also very similar. But those two groups are very dissimilar from each other. So we need some function that extracts information about the order of magnitude. It turns out that the log function does just that. The log function is, in a sense, related to roots and exponents. When we use exponents, we have the base and the exponent, which is the power we raise the base to. When we took the fifth root, we raised our base, the raw GDP number, to the power of 1 over 5. Roots are just inverse powers and vice versa. We can think of what we did as a sort of equality. Our GDP value raised to the power of 1 over 5 equals our output. But what if we kept the base the same instead and asked the inverse question? And let's make that base a number that will help us interpret magnitude. 10. What power would we need to raise 10 to get our GDP value? That's the question that log base 10 answers. And sure enough, if we take the log base 10 of our GDP values, we get a nice spread of values that reflects the variation in our original data. Moreover, our x-axis becomes a lot easier to interpret. Tuvalu, with a GDP of about $55 million, is about 7, almost 8 orders of magnitude bigger than 10. In the process of this squishing, we haven't destroyed any information. If we wanted to get back to our original values, we would just need to raise 10 to our output values. And now that we have relatively well-behaved datasets, we can think about scale some more. Maybe my theory suggests that relatively poor countries are more likely to experience war than relatively wealthy ones. In that case, I don't actually care about the raw order of magnitude difference between GDP numbers. I want to know where each country lies relative to the average and how far from the average they lie. And in fact, we covered just that in our previous module. But now we're not just interested in knowing the mean and standard deviation, we want to put them to work to tame this dataset some more. What I really want to measure is a country's GDP position relative to the average GDP. So after taking the log base 10, I'll find the mean of the resulting dataset and subtract that number from each value. You'll have noticed that we didn't change the shape of our distribution at all. We just moved it over so that the middle, or the mean, is over 0. Now when we interpret our variable, positive values are that many orders of magnitude bigger than the mean, while negative values are that many orders of magnitude smaller than the mean. This shifting is usually called centering your variable. One final step we can take is to scale our values in terms of the standard deviation. Orders of magnitude are useful, and for this dataset, they're a good unit to do our analysis in, but we might again be interested in the relative deviation from the mean. If we divide our numbers by the standard deviation of the set, we've scaled the data, so we can talk about the relative difference from the mean and relative variance. Now, that's a whole lot of work to wrangle just one variable, and halfway through the class, it'd be fair to ask why we're spending so much time on tasks like centering, scaling, and taking the log. Well, for one thing, this is what most of your work will look like if you choose to pursue a career in data analysis or data science. Data is messy, and you'll need tools to deal with that messiness. Variables don't often behave themselves, so the choices you make to address that misbehavior need to be scrutable. Another reason we've spent so much time building this foundation is that all of the more complex analysis we'll do in this class is built on your ability to interpret. Often, students are exposed to p-values and t-tests and, I believe, get the false impression that A, these tests provide some sort of objective signal from the heavens about the validity of your hypothesis, and that B, that they don't need to pay that much attention to the substance of what the tests are telling you. That's why we spend so much time on our interpretation, taking time to consider what we've done to our data and how that reflects in our analysis. Consider this week's reading in James Scott's Weapons of the Week. Scott also deals with misbehaving variables. Land ownership and tenure patterns aren't evenly distributed. To address this, Scott groups these variables together, usually into low, medium, and high categories. These aren't arbitrary choices. Scott's explanation for the phenomena he observes emphasizes inequality, and so his analysis transforms variables in a way that highlights the type of inequality his concepts suggest. The tables in the reading are simple, but they make the same compelling point, because Scott's method of measurement and data manipulation are consistent with his theory. And though Scott doesn't use many visualizations in his book, we certainly do, and we've seen how nonsensical visualizations look when we don't take care to transform our variables into useful metrics. Of course, in using the words transform and manipulate, I'm not using them in the sense that we do colloquially, meaning to wholesale change from its original value arbitrarily. Instead, we use those words to refer to the process of maintaining information in a dataset while focusing it on the relevant area of variation. ggplot and other plotting software can't do that for you. You need to think about and carefully decide how to transform your variables such that the relationships you've found become apparent. Moreover, you need to be transparent about the transformations you've applied. In the next module, as we move into covariance and correlation, these skills will become particularly important. Your ability to interpret covariance in the units supplied will serve you really well as we start to round out the class and get into linear regression. So let's summarize before wrapping up. Today, we discussed misbehaving variables and how to tame them. We talked about roots, logs, centering, and scaling, as well as the importance of interpretation. Next week, we'll move into covariance and correlation. I'm looking forward to seeing you in Module 5.